so many things we can do about the noise factors. That is, noise factors create the problems, start the fires, and defects and failures and quality problems. Now, as an engineer, what are the things we can do about the noise factors? And there are only four types of countermeasures we can apply against the noise. And this page, which is page 7 in your handout.
Finally, we got to one that they have.
Yes. Now, the one thing we could do is, of course, ignore noise. And one of my colleagues insists this is one of the countermeasures we can apply against noise. That is, he claims that some cases people are controlling certain things where they don't have to control. That is, if certain noise is not important, we don't have to control. We can ignore.
Interesting. Okay.
But however, most of the cases, ignoring is a problem. Later on, it's going to cause problem. Now, the second type of countermeasure is to control or eliminate the noise itself. For example, tighten the tolerance. Do you know this word?
Poka-yoke, yeah, mistake proofing. Used to be baka-yoke.
Yep, that's right. That's a Japanese word for food proofing, mistake proofing. And that certainly is a countermeasure. Right. And standardization, like operating standard, operation procedure standard, and so on and so forth. And these are controlling, eliminate the noise itself. And by definition, of course, some of these noise factors we cannot control. However, these are, if we will, traditional quality assurance activities. Like SPC is an excellent tool to get to this. That is, to control the special causes.
Just to identify that they exist.
Yeah, and to prevent the reoccurrence and so on, by improving the standard. And I'm not against doing these things. And like Poka-yoke, the simple investment of say $200 would say prevent the problem of $500,000.
Sure.
Then you should do that. However, overdoing can be a problem because this kind of countermeasure is cost-quality trade-off. Cost-quality trade-off. Okay. That is, whatever the countermeasure here, it's going to cost some money. And the idea is, if you're overdoing this, it's a problem. That is, if you think high quality means expensive, maybe you're thinking about trying to control and eliminate the noise itself. Another type of countermeasure, this one is something engineers love to do, compensation. Before the fact, after the fact. Say feedback control is you compensate after the fact. Like something like ABS. Example would be anti-lock brake system. It's nothing but it's a subsystem. It's a feedback control subsystem.
Yeah, this is something that Dr. Feigenbaum talks about extensively in his book on total quality control.
Oh, okay. And but ABS, adding ABS will increase the cost. But brake itself is not robust against ice. Therefore, they have to add the ABS. So of course, sometimes you have to do this. But again, this kind of countermeasure is a cost-quality trade-off. Feed-forward control, adaptive control, similar thing. That is...
this is adding complexity to the existing system to compensate for the inability of the system to be robust as it's currently designed.
That's right, exactly. This will make it robust. However, exactly.
But it adds complexity and cost.
Complex and expensive. And however, if certain noise is so dominating, we have to apply this kind of countermeasure. So usually we use so-called loss function to make decisions whether to do these two types of countermeasure. Now, the last type of countermeasure is something what we call parameter design. That is to minimize the impact of noise by changing control factor levels. And you have the best chance to reduce variability of the function without increasing cost.
Okay, so once you've identified what the various control parameters are, and you know specifically which ones you want to experiment with, then we go into this parameter design phase and set up the various parameters at the whatever number of levels we determine we want to test at, as using the orthogonal array in order to create the robust design that we're targeting for.